Welcome back to ECE 320A. In this particular video, we want to state and discuss some properties that are associated with transfer functions. And the first is that in our particular class, we're dealing with linear circuits, linear time invariant circuits. We have lumped parameters. By that, I'm meaning that we have discrete circuit elements, or we have R's, L's, and C's that are lumped into a single element for one resistor, another lumped for a second resistor, etc. But that's what I'm meaning by lumped parameter circuits. Those actually yield rational transfer functions or ratios of polynomials in S. When we have discrete components, those are the R's, L's, and C's, numerical values, those are lumped parameters. And that's in contrast to having distributed components, which you might think of as occurring if you were dealing with a transmission line type problem where you have inductance distributed over a physical length. And with transmission lines, those, in terms of solving those equations, now we're dealing with partial differential equations in the time domain. That's not what we're solving or analyzing or working with in this class. In this class, we're working with circuit elements governed or described by resistors, inductors, and capacitors. Those are lumped, meaning they are not a function of position or location, and that gives rise then to differential equations, not partial differential equations. That's the first property of transfer functions, is those ratios of polynomials in S are possible because we're dealing with RLC circuits, or circuits with lumped parameters. Another property of transfer functions that we've already uncovered is that if we want to find or identify or define transfer functions, we can do that using or assuming zero initial conditions. We're not interested in transient behavior. We're interested in input-output behavior, and because of that, we can neglect initial conditions when we're finding transfer functions of systems. Another property of transfer functions is related to the poles. The poles of H of S, those are the values of S that cause H of S to go unbounded. Those are actually going to be then the values of S that make the denominator vanish. In this example, our poles are at S equal to -1 and S equal to -6. And those particular values of S give rise to the natural response of the system. If you were to walk up to that system and hit it or kick it or excite it, then it naturally would want to behave consistent with these poles at S equal -1 and S equal -6. Or another way of saying that is it would have a natural response if we just excited this system, maybe with initial conditions. Then it would behave consistent with those poles. It would give rise to modes of e to the -1t and e to the -6t. And that's what we would have for a natural response. We go and shake it, and we get this system to respond with modes determined by the poles, and the poles of the system are at those values of s that cause the denominator to vanish. The denominator is a pretty special polynomial. It influences the poles. It also is then equal to the characteristic polynomial, which is giving rise to these natural modes and natural response of the system. In our example, we had a denominator polynomial in factored form given by the product of the factor s plus 1 times the factor s plus 6, or you might see that written as x squared plus 7s plus 6. That's now the characteristic polynomial that gives you the characteristic behavior of that circuit. If you went and shook it or excited it, it would naturally want to behave with these modes of e to the minus t and e to the minus 6t. Depending on what the roots of your denominator polynomial are, that will then influence your poles and the modes of your system. A stable system is a system that would naturally decay to 0. A stable system has all of its poles in the left half S-plane. All of the poles have real parts that have a negative value to them. They're in the complex S-plane in the left half plane. And in our particular case, our circuits that are passive, meaning we don't have any op-amps in those, are RLC networks that are passive naturally will be producing stable transfer functions, or transfer functions that have all of their poles in the left half plane. We've now talked about poles. Let's talk about zeros. The finite zeros of a transfer function are the roots of the numerator polynomial of that system, or transfer function, h of s. The finite zeros are the finite values of s that cause h of s to vanish or equal 0. We can also classify systems as minimum phase and non-minimum phase if we have a stable system. Stable means all of the poles are in the left half plane. If we not only have all of the poles in the left half plane, but we also have all of the finite zeros, all of the values of s that cause the numerator to vanish, if they too are all in the left half plane, then we refer to that system as being minimum phase. So a minimum phase system has all of its poles and all of its zeros in the left half plane. Let's look at an example, and this will start to make more sense as we get into Bode plots and frequency response, but our Bode plots will be we will sketch Bode plots. We will restrict our Bode plot sketches to being of minimum phase systems. That means we will have systems with all of our poles and all of our zeros in the left half plane. So to make that connection, let's just see what happens. Now, here's one example system, h sub 1 of s. It has a finite zero at s equal to minus 1. That's the blue circle. And it has complex conjugate poles at minus 2 plus and minus j1. And I've indicated those with blue poles. Compare that now with a mirror-imaged 0. Let's say now we have a system, h sub 2, that has a 0 at positive 1. That would then have a factor of s minus 1 in its numerator. And suppose that it has poles at minus 2 plus and minus j1, the same pole locations as they are in h1. Both of these systems are stable. h1 and h2 are both stable, but h1 is minimum phase, because it's 0. If you evaluate that numerator, set it equal to 0, and evaluate s, you'll find s is equal to minus 1. It has a 0 in the left half plane. In addition to being stable. H sub 2 is a non-minimum phase system because its numerator actually has a finite value of s that vanishes, or the numerator vanishes for a finite value of s with s equaling 1. That's now in the right half plane. That's now a non-minimum phase 0. And where does this minimum and non-minimum phase come into play? We are going to learn that the phase associated with this, let's say the 0 at minus 1, is determined by this angle theta. And that phase of this factor at s plus 1 is going to be, so theta is now the angle that has a tangent of omega x, the imaginary part, divided by the real part, which is 1. So theta is now the inverse tangent of omega s over 1. Now, if you look at theta sub n, its angle, theta sub n, I hope you can see that these angles are all defined with respect to a horizontal line going off positive to the right. Theta is smaller than theta sub n. Theta sub n is actually, let's say that it's now 180 degrees minus the angle here. So theta sub n is going to be 180 degrees minus an angle that has an inverse tangent of omega x over 1. And I hope you can see that just visually, theta sub n is an angle that's bigger than 90. Theta is an angle that's less than 90. Theta sub n, no matter what omega sub x is, these zeros would give rise to the same magnitude, the length of the hypotenuse on the left and the length of the hypotenuse on the right. That's always the same for a given omega sub s, and that determines the magnitude contribution of those zeros. So the magnitude of those zeros, be it at minus 1 or plus 1, is the same. So we couldn't tell any difference in the magnitude response, but the angle is different. The angle of the blue 0, or the 0 in the left half plane, is smaller, so it's minimum relative to the same magnitude response. The angle due to the 0 in the right half plane at plus 1 is bigger than 90. The angle of the 0 in the left half plane is less than 90, so the angle due to the 0 in the left half plane is minimum phase relative to having the same magnitude response. And that's where this minimum phase and non-minimum phase comes from. If we looked at mirror images of zeros, the zeros in the left half plane would have an angle or a phase that's smaller than its mirror image in the right half plane. That's what's driving this definition or this terminology of minimum phase and non-minimum phase. That will become important when we start doing Bode plots or frequency response. We will be doing that we will restrict our introduction to Bode plots to be of minimum phase systems. If we looked at the frequency response, which is the Bode plot, that's found by evaluating, I should have gone all the way up that imaginary axis. That's looking at the angle and phase contribution of all of these poles and zeros as we walk up the imaginary axis, or when we look at or evaluate a transfer function, h of s, for values of s equal to j omega. This is now walking up as we vary omega from 0 to infinity. We're now walking up the imaginary axis. Or we're looking at h sub 1 of j omega, or everywhere we had an s in the transfer function h sub 1, we replace that s with j omega. Here, if we go ahead and factor the denominator quadratic into its complex factors, we now have a pole at minus 2 plus j and a pole at minus 2 minus j. We replace s with j omega, and now we want to find what is the complex number associated with h sub 1 of j omega for a particular omega. If you plug in omega equal to, let's say, 1/2, you would now have a complex number in the numerator divided by a product of complex numbers in the denominator. But you could, for each of those factors, find the magnitude and angle just by using the polar form of these complex numbers. And once we have the polar form, it's easy to find the magnitude of a rational expression because it's now just the product and division or quotient of those magnitudes, and we just have to add and subtract angles. In this case, the magnitude of our numerator would be the magnitude of the real part, which is 1, plus j omega. So if we wanted the magnitude, it would be 1 squared plus omega squared square root. It's the hypotenuse of that particular factor. In this case, the magnitude would just be the length of that line, which is the hypotenuse. It's the real part squared plus the imaginary part squared, square rooted. That's now the magnitude of j omega plus 1. The angle is the angle that has a tangent of omega, the vertical distance, over the horizontal distance, omega over 1. Similarly, for each of the two factors in the denominator, one of the factors is due to the pole in the second quadrant, the other factor, which is this magnitude and angle, and the other factor has a magnitude and angle associated with the pole in the third quadrant. For a given omega, you can now evaluate that magnitude. That's just another hypotenuse of a right triangle dependent on the frequency omega, and the angle is also dependent on the frequency omega, but it's just a straightforward computation to find those magnitudes and angles, and that now produces how this transfer function behaves for a given frequency. Meaning, if we now excited this system at, let's say, a frequency of 3 radians per second, we would now want to find what are the contributions, magnitude and angle, of each of these factors at that frequency, 3 radians per second. We could plug in 3 now down here for omega, evaluate that, and that would give us how this particular transfer function either amplifies or attenuates, depending on the magnitude, if it's bigger than 1 or less than 1, and how the angle, the phase, or how this waveform is shifted in time at a sinusoidal excitation of 3 radians per second. If we were to excite this system that has 2 complex conjugate poles and 1 0, using a cosine waveform at 3 radians per second, that's what evaluating at J3 means, then we will see that that cosine of 3t gets modified by how this system behaves at that frequency, omega equal to 3. And whether it's amplified or attenuated and how it's shifted in time depends on the magnitude and the angle of this expression at omega equal to 3. That will now be what we need to take into our understanding when we start talking about Bode plots in subsequent videos.